We continue where we left off yesterday. That is self assembled monolayers, which is also SAM is an acronym, though SAM is an acronym for a much more lethal weapon, surface to air missiles. But what I left off yesterday was that there would be a surface on which these chains would adhere. When in ceramic fabrication, it has been seen that this chain length should have 9 carbon atoms optimally. Why? This produces optimal van der Waals interaction. If the chain lengths are larger than say 20, there is a problem of solubility in organic solvents. Before I start the lecture, let me start talking of how to fabricate a structure, self-assembled monolayer structure on, say, silicon substrate. Any material which you see around in this room has a layer of dust, has a layer of moisture, has our all body oils. Even if I tear this paper, even as I have tore this paper, it has immediately been covered with moisture, the body oil I am emanating, and hence when we are talking of self-assembled monolayers, one of the first things that is required is an ultra clean surface. What I want to do is, I want to do siloxane anchored on silicon. The first thing that we have to do is clean the silicon surface, and it is done, this cleaning is done by what is called a Pirhana solution. This Pirhana solution, or rather, Pirnaha solution. This Pirnaha solution is really a mixture of concentrated sulfuric acid, nitric acid. It just eats away whatever is there on the silicon substrate. So, what is this done is, first the silicon substrate is dipped in this solution and then washed with deionized water repeatedly. This solution actually is so reactive that I would rather use today H2SO4 H2O2. If I use nitric acid, that compound, it's just very, very reactive. Disposal is a major problem. And so what is done today is a mixture of sulfuric acid and hydrogen peroxide. What does this do? This, if this is the silicon substrate, there are silicon atoms on the surface. Within the substrate, the scale is very, very, very exaggerated, and what it does is basically it leaves behind this sort of a surface at the top, this sort of a surface. This is basically, it cleans away the surface, activates the surface, leaving behind a hydrolyzed layer of silicon. This allows us, for example, let me redraw this again. This sort of a hydrolyzed surface. Now, if I take this substrate and dip it into, say, this sort of a thing, what would happen is deposition would occur. Forming this, and then this would transform to basically, in fact, this is a self-assembled monolayer over by itself as of now, and this would transform so that these chains pack very optimally. You see, after, there are a lot of things we can do with this. After this has been formed, we can change these Z to some other side group. It's a simple organic organic reaction to have this Z replaced by say X, in which case we will have and this goes on. I can replace this X by Z, and this is basically what SAM is all about, self-assembled monolayer is all about. Let me talk of now real life cases, how these are applied in ceramics. You see, if let us say we have a substrate, this has been immersed in solution. So, this is where the solution is. Let us say these are the ions in solution. If in self-assembled monolayers, there are two possibilities. Just as I had shown over here, that this head coupled with this head, these ions can deposit on the substrate by itself, or these ions can undergo hydrolysis, they can undergo condensation, or followed by nucleation to give a colloidal particle. Which could deposit on this in the form of clusters. Now, what if we are looking at this particular path? There I have got ions, the ions have hydrolyzed, they have nucleated in solution, and these nuclei are depositing on the surface. Then the type of self-assembled monolayers we would get is, if I look at it under a microscope, if there is a field of view of the microscope, I would see that there are clusters over here. It depends on where the surface is active, because here in this example I had said I had to take the silicon, activate its surface, that is, create these groups. This is surface activation, so that this coupling could occur. So, here if I am talking of clusters, it depends on where I have activated the surface. But this is not what I wish to focus upon, but I rather would wish to focus upon this part, where the ions deposit on the surface without forming colloids. It is the ions depositing on the surface. Yes, the films will be polycrystalline, and a lot of work has been done on such deposition processes. But fundamentally, let me deal with what are the issues. Is first of all, formation of zero charge precursor. Let us say M is a metal ion, This is the zero charge precursor, followed by nucleation, growth, and aging. Now, the very first step in formation of SAM, the first step, which was formation of the zero charge compound, is combined with a deprotonation reaction of the metal cations which are solvated by water molecules. In this particular way. Now, this reaction obviously depends on acid concentration, and can be influenced by complexation with anions. But this allows us to control the precipitation from the solution. This is what happens if it complexes with this anion. The creation and growth of the oxide based nuclei by further condensation involves olation. This is olation, and so the further condensation leads to either olation or oxalation. Further aging if the material is aged further, Oswald ripening occurs and agglomeration happens. Basically, if I am following this clusters, this is not what I want, but this happens because of the processes that I have described over here. Now, can we deposit thin films of ceramic oxides on substrates? Let's take the case of, say, titania. Titania exists in anatase and rutile form. Let us see how are these shapes formed. I give up. Let's see if I can get it directly off. You see, these are the basic titania octahedra. These are the basic titania octahedra. The octahedra here combines edge to edge over here. Now, when the third octahedra combines, this is the third one. It can either form edge to edge in this linear fashion, or it can combine edge to edge in this particular fashion. This is the structure of rutile and this is the structure of anatase. Now, let us try to look at, if we try to self-assemble this titania thin film, what is it that we will get? You see, the first thing, that is, we start off with titanium tetrachloride, hydrolyze it, and the zero charge precursor this is formed. Now, this zero charge precursor combines together to give a dimer, which should be two of these will give you this particular material. Now, here the octahedra of the two titania. Remember, this titania is inside this is a titanium octahedra. I am combining two of these titanium octahedra over here, and here they combine together. Here they share an edge, they form an oxo bridge, which are basically this. So, if I have to get self-assembled monolayers of titania, I have to go through this process where TiO6 octahedra, which are over here, grow on the surface by oxalation. This is an oxalation process. And finally, what is the structure we will expect? You see, the thing is, over here when I showed in the diagram, rutile is a long one octahedra sharing an edge with another octahedra in a linear fashion. But in anatase, they share the edge all right, but it is not linear. So, the anatase one will form smaller chains than the rutile, and hence anatase will be more stable than rutile while self-assembly. So, if we take titanium tetrachloride and use it for self-assembled monolayer formation, what we will get always is an anatase layer on the substrate if we follow the procedure correctly. And the way to do it is to hydrolyze it, form the zero charge substrate, let them combine to give the oxalation. These oxalation products deposit on the surface, they grow by Oswald ripening, and finally they cover the entire surface. However, if you think that all that you will do is take a beaker, put in a solution of TiCl4, then hydrolyze it, and have your substrate somewhere over here. This is your substrate, and the substrate will get a good coating of anatase. You are wrong. The reason simply is, this is a stationary substrate, and as deposition occurs, the local concentration of the titania over here falls, and as a result the deposition rate slows down. Hence, in such cases, if we have a beaker in which we have kept the substrate immersed, we will not get any SAM film greater than, I would say, 10 nanometers. SAM film greater than 10 nanometers is impossible using this configuration. What configuration? I got a beaker, I put the titanium tetrachloride in it, slowly hydrolyze it, put my substrate in. Well, I will have films which are no thicker than 10 or less or equal to 10 nanometers. But does it mean that we cannot grow films thicker than 10 nanometers? The answer is yes. But then the process has to be devised where the solution continually replenishes itself. So what we can do is we can have a tube, a cylindrical one, where basically the solution flows the surface. This is the substrate, this is the substrate, and well, as the solution flows, this amount of the ions at the surface is refurbished, unlike in this case where the solution was stagnant. So after deposition, the amount of titanium tetrachloride decreased, hence further film growth stopped. In this particular case, if we have a flowing assembly, this problem of thin film, of only ultra thin films being deposited can be resolved. And using this flow process, films as great as 2 micrometers has been fabricated. In fact, my students routinely fabricate this 2 micrometer thin film in the laboratory. If they are using a configuration where the solution keeps constantly flowing and the material keeps on depositing. I think I would stop here as far as self-assembled monolayers are concerned. But I would still stick to molecular engineering route for ceramics. And what I would do is, when I am talking of molecular engineering, I will molecularly engineer the ceramics itself. All of you have seen mica. It's a mineral which comes out in the form of thin sheets. Basically, this is the structure of mica. The legends are given. It's based on SiOH tetrahedra with some Si being replaced by aluminium. Now, mica I have taken, I could have taken kaolin also. But mica I have taken is simply because I can look at only the individual thin sheets of mica which has length of 9.94 angstrom, which is on the y axis you can see that is the unit cell I can think of considering. And what will I do? Here there is an octahedral sheet sandwiched between two tetrahedral layers. What we can think of is another compound which is like mica, where again an octahedral sheet is sandwiched between two tetrahedral ones. The bottom sheet is tetrahedral, the top sheet is tetrahedral, in the middle is the octahedral sheet. The tetrahedral sheets are fundamentally of silicon and aluminum, while the octahedral sheets are, okay, let me write down tetrahedral sheets, silicon, aluminum, while the octahedral layer can have any of these, one or more of this. If I look back at the screen, what I will see is these magnesia, iron, they occupy right inside the octahedral sheets only, inside the octahedral layer only, or this over here. These are the octahedral layers. Sodium can go in over there, potassium, calcium can also go over there. So, what are these? These are basically exchangeable cations. The structure I referred to was montmorillonite. It has got a tetrahedral sheet, an octahedral sheet and a tetrahedral sheet. The octahedral sheet has exchangeable cations. What is the implication of these exchangeable cations? What the implication is basically that I can, by putting in larger cations in the octahedral layer, I can swell the mica layer with the montmorillonite. Because if I have larger cations in the octahedral layer, the tetrahedral layers would separate out more. This is the one property I will use for talking on how I am going to molecularly engineer them. We could exchange these cations for anything. What I would be now really building my lecture on today would be based on brucite layer. This is magnesium hydroxide. And I will take this lecture to a place where I will show how by changing the spaces between these layers, I can do a lot of engineering with these layered ceramics. Now, what I have talked of montmorillonite, what I have said I shall do with brucite is applicable in many cases to clays. Montmorillonite is a clay, mica is a type of one, where we have got Si, Al, OH ions repeat in octahedral and tetrahedral positions, which repeat themselves in space. and we have cations which are exchangeable. Now, when we are talking of clays, hence we are talking of an arrangement of a tetrahedra and octahedra. There can be various types. For example, pyrophyllite, the layer type is di-octahedral and its composition is ideal one, ideal composition. It has got dioctahedral structure, 2 octahedra. Whereas talc is a body powder you use, the powder you use on a body. It's a mineral. It is trioctahedral and its formula, idealized formula is now these two form a particular group. Montmorillonite, you thought these were complex? Look at how complex formulas I'll have to write down. Yep, that's Montmorillonite. That's another type of structure. In this, you have got various variations. Let me give you some names. It is also dioctahedral. This is another group of compounds. The third group of compounds belong to vermiculite, which can be dioctahedral, or it could be trioctahedral. These are all two-dimensional heterostructures of clays. And in each case, there are exchangeable cations. By exchanging the cations, we have the possibility of increasing the layer width, swelling it up, incorporating more new things for different application. For example, you have seen the polythene sheets, very soft. What is now being attempted or is being done is, if these are layers of clay, this is called intercalation. Polymer chain is intercalated between the layers of the ceramics. It can be mica, it can be vermiculite, it can be montmorillonite groups, or it could be something else. These are clay platelets. The polymers are all here. This is delaminated. Why delaminated? Because this ordered structure of the clay planes have been destroyed by the polymer group, and virtually between here and here the difference is delamination has occurred. So, this polymer clay, which people refer to it as polymer clay nanohybrid, they can be synthesized either by intercalation or in this disordered form. For that, what you have to do is take the clay and then have the clay particles exfoliated so that they open up. So, if we have, say, kaolinite, let me take kaolin. This is exfoliated so that the basal spacing between the kaolin planes increase. And I want to introduce polyethylene. I am deliberately using polyethylene because polyethylene is non-polar while clay is highly polar. So, first of all, here surface activation has to be done, and this is done by adding quaternary compounds to clay. The surface activation is there. Why is surface activation required? Because without surface activation, non-polar like molecules like polyethylene will not adhere to the surface. So, this surface again has this surface activation requires a compound which has a non-polar group at one end and a highly polar group at the other. The highly polar group will adhere to the clay layer, while the non-polar group will dangle, and that non-polar group is the cause why polyethylene will slide between the clay layers to give you an intercalated structure. Now, this sort of work is being done by polymer chemists worldwide over to get stronger and stronger polymers. A lot of the current polymer, for example, the polymer which is used for your helmets, perspex, that is an environmental hazard. A lot of the polymers we use are environmentally hazardous. The housing of the car headlights, as they are made now, they are made from a polymer which is hazardous. How good would it be to have that headlight housing made from a more benign polymer like say polyethylene? But the difficulty is polyethylene is a soft material with a low glass transition temperature. So, what people are working on is intercalation of clays with polyethylene, so that the polyethylene gets strengthened. It is a much more benign product and hence can be used as the housing of the car headlights. Now, this sort of a molecular engineering with ceramics is just the order of the day. The polymer chemists have shown the way, and now after the break I shall deal with it, how ceramics are employing such intercalation to give you hybrid products in various fields. Obviously, everyone wants to have a tag. Hey, what are you working on? I am working on organic clay nanohybrids. Big sounding name. Yet, we have long ways to go. I'll come back to this after the intermission.